Good morning, everyone. Took me a second to get loaded up there. I'm interested in talking about today the disparate kinds of domain data that might go into machine learning in solving some of the problems we have in hydrology and catchment problems. And I am part of the University of Minnesota-led KGML project. And I'll start off by telling you a little bit about my role. My role in this project is as domain scientist. I'm a modeler and a data analyst for hydrology for my career, and a collaborator with the University of Minnesota KGML science team in developing these new approaches to guiding physical understanding of hydrologic sciences. In this talk, we'll explore some essentially an ideal example where KGML might utilize co-located climatic, hydrologic, geologic, and ecosystem data and models, basically at an NSF-funded critical zone observatory that is linked to the historical climate reanalysis from NOAA and NASA. My work, just as an aside, my work environment uses e-notebooks, in particular Mathematica, for data analytics. And I make the comment because I believe the utility of notebooks for compiling, executing, and sharing the results of KGML is going to be important in the future for our colleagues to make advances as well. The overview, my objective is to develop a class of emulators that integrate global climate, land atmosphere data with high resolution experimental watershed data and models. My goal would be to apply KGML to advanced predictive understanding, building on current data models and state-of-the-art catchment information. Okay, a few questions. Won't be able to answer all these, but I think these are very relevant to the problems at hand. Can models and data from multiple physical domains, multiple resolutions and scales be effectively integrated in KGML? And from some of the talks we've heard today, that question may already have been answered. I don't know. What is the value of KGML in transferring trained nets to ungauged catchments? Still an issue, but again, there's some promising aspects of the earlier talks. Can we improve our biases and in particular uncertainties in the model? Once again, we're hearing that some of these things are well on their way. And one question I have for all of the presenters and maybe some attendees too, what are the essential data required for KGML? And how can we elicit sort of the community collaboration and the sharing and transfer of this knowledge? Okay, well, maybe I won't spend much time here, but hydrology and watershed science has a huge potential impact and is obviously related to the water balance changes as we have deforestation, urbanization, and climate change. Food security and supply is directly related to the hydrologic cycle on the land, as well as in the atmosphere, ecosystem services, floods, droughts, water supply, and then water quality. So modeling schemes. What are the opportunities for KGML in our project? And I make the point that all models should be made and implemented with a purpose. We have point models such as soil profile models or soil pack and snowmelt models, aggregate models such as SWOT that integrate over spatial dimensions and capture the aggregate effects. And then we have space-time distributed models that attempt to solve systems of PDEs for processes operating in the catchment. The interesting next step is sort of how do we link these kind of model information and their purposes and the data that goes with them into for example, network models, meta models, emulators, and I'll also bring in here reanalysis. Climate reanalysis is an important kind of data model structure that we make a lot of use of. And then finally, what are the products from this and how do we get them from data assimilation, prediction, and scenario development? Okay, well, I think network models, meta models, emulators, and reanalysis deserves a special look, and we'll, in terms of KGML, and we'll look a little bit at an example of that. Land data assimilation systems from NASA and NOAA or climate reanalysis are used globally to get the atmospheric inputs to hydrologic systems. Climate reanalysis gives numerical representation of the historical climate. It assimilates past observations from weather stations and land surface data, satellite information, many other soils data, and even the vegetation and snowpack from satellites, for example. So it is a composite of not just numerical models, but all the collected data. What it's missing, in a way, is watershed and river basin data. And the other point I want to focus on in this talk is the role of experimental watersheds in making the connection. And that is colocation of instrumentation. Let's think of that as bedrock through boundary layer, where we have sites, experimental sites that measure all the variables in a co-located sense. Maybe another opportunity, and I'll try to make that case here. The Shale Hills Critical Zone Observatory in central Pennsylvania near the Penn State campus is the example I'll use. And it actually started as an experimental forest research station back in the 60s and 70s. So there is historical data as well. Then there's the Critical Zone Observatories are a national and even a global network of observatories where Earth system models are being instrumented and simulations models are implemented and developed on hydrology, water quality, geochemistry, geomorphology, etc. The Shale Hills experiment. This is only 8 hectares, and these are all sample sites. The little tiny dots are the ecologists went out and did biomass estimates and tree height measurements. It's a forested site, and they measured all the trees for their mass and height and other characteristics. There's weather stations here. However, it is an experiment. It's a short-term experiment. This part of the data was implemented from about 2008 through 2013 or 14. Or 15 maybe, and so there's groundwater data co-located with soil moisture profile data, as well as stream flow data, etc. So you get an idea of the co-location as having a lot of variables to begin to test some of these tools. Here's gives you an idea of the geology. It's a shale under deeply dipping shales with regoliths where most of the water accumulates as groundwater. The models I'll talk about in a moment uses an unstructured grid. The upper left is a LiDAR image, 0.5 meter LiDAR over the watershed. The upper right is the soil type. The lower left is the soil depth, and the vegetation is figure 4. The PIM model is a distributed model that takes a system of PDEs, solves the PDEs and ODEs for vegetation, surface runoff in 2D, unsaturated flow and saturated flow over this unstructured grid using a finite volume, semi-discrete approach. Okay, so what do we get? Well, what we did was run a data reanalysis for the later part of the record when we had the CZO data and did ensemble Kalman filter. That was Yuning Shi in his work in WRR, and estimated the hydraulic properties of soils with the data assimilation and then other parameters as well. And then we ran a reanalysis from 79, in this case, to 2010, that gives us the precipitation, stream flow simulation. This is a reanalysis, of course, is a combination of data and model. And so in that sense, it's an ideal data set to begin to test. some of these machine learning tools. Okay, so there's the groundwater signal, the soil moisture storage signal, recharge, and evapotranspiration components, canopy interception, blah, blah, blah. Okay. So what do we do with it? A product that everybody wanted to try, and this is Juan Yu's work, where we took that historical simulation record for this small catchment and mapped out a storm library where all the tropical storms and hurricanes that had an impact on the watershed, we pulled out. And you can see in the rainfall runoff curves in each of these, for each of the storms listed here. So this is just one kind of thing one can do. And there's a lot of reasons why a storm library like this could be valuable to studying things like climate change or land use change and that sort of thing. Okay, so the simple model of extending this strategy, here's just a elementary LSTM that we tried with 2 inputs, precipitation and evaporation. The idea here is to see whether or not the machine learning tools can learn from the historical data as well as the reanalysis data. And so here's a reanalysis training data set we used from 1979 to 99 that's showing rainfall and runoff at Shale Hills. And then here's the training experiment using the pre-CZO or pre-detailed observation experimental data, and simply using reanalysis and the hydrologic model as the two inputs and outputs. We then ran the neural net on those inputs and outputs, and you can see from the observed as the dots and the predicted, it looks pretty good. And however, when testing, we see, this is on the 2000 to 2013, we basically see a serious deterioration. So what you might take from this is just one of many examples that we're planning, but I wanted to point this one out because we're simply using the reanalysis to drive the model. And that's what most people tend to do when they use hydrologic models on a continental scale. And this is telling us, well, maybe that's not such a good idea. And we know that this later period has better data because we've been observing it for those many years. It's not model data anymore. It's really biased towards the real data. Okay, well, this is just a net train result that shows the quality of the training results, but we also should look at histograms of training and test simulations. The training data looks good. It captures the peaks, it captures the high values and the low values, where the testing data is really falling apart, and especially giving a lot of negative numbers here, which can be fixed easily enough, but it's still not going to get entirely get the data itself. Okay, so what are the next step in this process? We think this is a good experiments along these lines using assimilated data and models, and the physical model with reanalysis is an important product. I'm not trying to argue against that. What we need to do is to make this work at the small scale and scale it up to complex river basins. An example we're doing on another project as part of the DARPA World Modelers project is looking at really lightly gauged or ungauged basins in Ethiopia. This is a sub-basin of the Blue Nile in central Ethiopia. And the idea, of course, is we're going to have a lot less data. And there we've simply always have used reanalysis. So we've got to learn some things about what it is we can do in these sparse data settings, because in these areas, it's crucial to be able to do a better job of predictions. And we're always going to have limited data, at least on the ground. We have better prospects for satellites in the atmosphere and atmospheric information. Okay, so how do we go about that? Well, we've heard some ideas about this, but this is just some work of Ibrahim Damir and at Iowa. Basically, this is a nice article that talks about the hierarchical data model as a graph network. And we think this is a very nice way to begin to think about scaling up to the system. And we'll be doing something along those lines as well. As a matter of fact, there already are. My summary of this in this very brief and high level look at things is it is the ability of the machine learning to help us recover information from experimental data, very disparate kinds of data from experiments that have been done by earth scientists, hydrologists, and others, and integrating that into historical knowledge for KGML prediction. I think that could be a very important tool to recover some of this information into our modeling for future. Some values, rapid reconstruction of flood and drought response. I made a little case for that earlier. I'd like to know how good they are, and that would be a thing we could do. Ensembles of initial conditions for floods and droughts, we certainly need to think about how that can be done, and then to address uncertainty in weather and climate. Our challenges are manifold, but a few of them are just in extending and improving climate reanalysis with hydrological and ecosystem observation or in geomorphological observations. I noted that very little discussion was made about anything about the deeper than the soil profile in many of the talks. And I think the subsurface geology and the terrain geomorphology is an important element, I think, that there is data for. Design of machine learning tools for multi-domain data and models will have to be given some serious thought, I think. The river basin infrastructure management of municipal, industrial, agricultural, reservoirs, power systems, et cetera, is another huge challenge, and that's been discussed today. I think the Ethiopia example just makes the point, I think, of we need to think about providing international leadership for global water resources. And I thank you for your attention.
Thank you very much, Chris, for your presentation. There's just one comment that was posted. Maybe other questions will come, or questions will come later. But this question was that the person wants to point out a DOE experiment next year, which has very common themes for your Bedrock PBL. And the website, the link to the website for that is in Slido. So anybody interested in that can find that.
Oh, I think that's a very good idea. You know, in some sense, we're searching on a continental and a global scale for how this idea of integrating models, data, and machine learning will work. We can prove or disprove that only in a true experiment where most things are available and measured. And I think that's the point, the underlying point. It sounds like the DOE's got a good idea to advance on that front. So.
Yep. Okay, thank you very much, Chris.